before, we are going to look at compressions and expansions. A generic term for this is a stretch. Either we're shrinking it down, called a compression, or we're expanding it, called a expansion, sorry. But the general term is stretch. So in order to visually understand what's going on, we're going to focus on a base function. So this is one of the things we did on day one. The square root of x. Let's make a table of values for our key points. If x is 0, y is 0. If x is 1, 1. If x is 4, 2, and 9, 3. Beautiful. Let's graph those. 0, 0, 1, 1, 4, 2, and then 3 plus 3 is 10. There we go. Just going to make sure I did that correct. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So this is a base function. Square root of x. We can do this. We should have this memorized. When you see square root of x, you should be able to plot these 4 points. And you should know that the shape is a half parabola on its side. Okay? So what we're going to do now is we're going to stretch it. We are going to put a 2 in front of the y. And we're going to make a new table of values. However, I'm going to start by drawing my base function first. 2, 4, 6. There we go. So there's my base function, square root of x. I'm going to switch colors so we don't confuse it with our stretched version. Okay, so now to find my y, it is 2 times the square root of x. So if x is 0, what's my y? 0. If x is 1, 2. If it's 4, 4. If it's 9, 6. Right? Square root of 9 is 3. 3 times 2 is 6. So let's graph these points. 0, 0. 1, 2. 4, 4. 9, 6. I have not changed my x values. I have simply stretched my y values. Okay, so I've essentially made my graph taller. So in my function, this is what I have done. I have taken my y and I have replaced it with 1/2 y. Well, if y equals root x, then 1/2 y equals root x. So I'm replacing it right there. And when I solve for y, right, I multiply both sides by 2 and I end up with 2 root x. So when I do the replacement, I have to think of it as upside down. If I replace y with 1/2 y, I am doubling the outcome, because when I solve for y, it's going to be 2 times the square root of x, or 2 times the function. Okay, and then in our third example, I'm doing exactly the same thing. If I have 2y equals the square root of x, then when I solve for y, I'm going to get 1/2 square root of x. I end up with a reciprocal there, right? And so when I have a reciprocal, then I have a compression. I'm going to be making it smaller. So what would the picture look like? Again, we're going to start with our base graph. 0, 0, 1, 1, 4, 2, 2, 4, 6, 9, 3. My base function, square root x. And again, using a different color, I'm going to determine what is my y. So I'm taking 1/2 times the square root of x. So if x is 0, y is 0. If x is 1, 1/2. Now, when we're looking just algebraically, we're going to leave it as fractions. However, because I want to graph it, it's easier to work with decimals. So this is 0.5. If x is 4, 2, And if x is 9, 3/2 or 1.5. Right? And so again, let's graph our compression 0, 0, 1.5, 4, and 2. Oh, did I make a mistake somewhere? Ah, yes, thank you. X is 4, gives me square root 2, but then I divide it by 2, gives me 1. Yes, thank you. All right, and then 9 would be 1.5, so somewhere here. We're just estimating. Okay, so my x values do not change when I put a coefficient in front of our function. The coefficient in front of the function tells us what we're doing. If it's a small fraction, you are dividing by your denominator, whatever the denominator is. If it's a whole number like we had up here, you are then multiplying your function by that. Okay? So let's talk about coordinate mapping. Okay, if these are my new functions, then my original xy would be mapped to what? How would the coordinates change here? I'll give you a hint, x doesn't. What are we doing with the y? 5y, right? Y equals 5 times the function, so it's 5 times the y. Okay, next one, xy, x, and? Okay, so different ways we can write this. 1/4y, so 1/4 times y. Or we can say y/4. Or if you want to be really explicit, you can say y divided by 4. All of those things mean the same thing, but there's different ways we can write it. Okay, next one. X, y goes to what? There's an extra piece there now. Ah, yes, -2y. Anything change with the x? No. Okay, what does the negative tell you? This is telling us two pieces of information. What is it? Reflection. So it's upside down. Oh, upside down. And it is expanded by 2. Right, the negative tells us there's a reflection and an expansion or a stretch. Okay, what would the next one look like? Again, pay attention, there's extra pieces of information here. Negative x, 3/4 y. So again here I have a reflection, but now it is backward, right, over the y-axis. And 3/4, am I getting smaller or bigger? Smaller, so I have a compression. Okay, so 2 bits of information there. The negatives are always part of the coefficient. So if you have a positive number, you're going to have either a compression or expansion. If you have a negative number, you have a compression, expansion, and a flip. Yes.
For parabolas, when it's a fraction, does it actually
Yes.
get bigger though?
In this case, it would get smaller because 3/4 is less than 1. But yes, it would get smaller and bigger. And we'll do an example of it in a second. Yes, it will affect all and any graphs. All right, let's flip the page. Okay, we are given a function. We do not know what the function is, but we do know what it looks like. So we need to use our coordinate mapping in order to be able to do this next activity. So let's identify what are my 3 key points. The first one is 0, -5. Then I have, nope, I did that wrong. What's the first coordinate? -5, 0, right? X first, then Y. Then I have 0, 2, and then I have +5, -5. Those are my 3 key points on my base function. Okay, so this is the base function. We don't know what it is, but we know what it looks like. Here, we are asked to do a transformation. The 3 is on the outside, so what is this transformation? What are we doing? Expansion. Okay, so when I do my coordinate mapping, x, y is going to be mapped to what? X, 3y. So I'm taking my y coordinates and multiplying by 3, and I don't touch the x ones. So what does that look like? If I have -5, 0, where's the new coordinate? -5, 0. Because 0 times 3 is still 0. We do not touch the x coordinate. Okay, 0, 2 is where? 0, 6. Right, multiplying only the y value by 3, and then where's my last coordinate? -5, -15, so it's like way down here. Oh, no, not -5. +5. -15, so a little bit off the charts, and that's okay. Math is off the charts. Thank you. I appreciate the pity laughs. I'm good with that. All right, so we have not touched the x values. We've only expanded the y values because the 3 is on the outside. There's nothing on the inside. There's no negatives we have to worry about, so we can move on. All right, similar situation here. We have a 1/2 on the outside, so what is my coordinate mapping? XY goes to x 1/2 y, or y over 2. That's fine as well. Okay, rather than me scrolling up and down, can I just trust you guys to tell me where are my 3 key points? -5, 0. Then 0, 1. And compression. My original point is at 0, 2. Your y value divided by 2 would be 2 divided by 2 is 1. So 0, 1 is correct. Where's my third point? 5, -2.5. Yes. You could also write it as 5, -5 over 2, which mathematically makes sense, but when we go to graph it, sometimes hard to see, right? So using decimals is useful. All right. So again, we've squished it down. This is a compression. All right, last example. Now I'm going to take my XY coordinates. What are we doing here? It's a reflection, and is the negative going to be on the X or the Y? It's going to be on the Y because it's on the outside. So this is X minus 2Y, or -2 times Y. Okay, again, focusing on the Y coordinate, where is my first point? -5, 0. Where's my second point? 0, -4. Right, it's a reflection. We're expecting a flip, so we're going from the top half to the bottom half. And my last coordinate? 5, 5, 5 or 5, 10? 5, 10. 5, 10. So it is twice the height and upside down. So this is expansion and reflection. And you would say reflection over the x-axis. or you can say upside down. Either of those is all right with me for now. Okay, now a vocabulary word is coming up, so let's take a look at the bottom of our page. An invariant point. A point that does not change is a point that is not affected by a transformation. Based on the transformations that we just did, which one of the 3 points was our invariant? -5, 0. Okay, why do you think that that point did not change? Because the y is 0. So when we have a vertical compression or reflection, if you have a point with a y of 0, meaning it is on the x-axis, it is not going to be affected because you can multiply 0 by whatever you want, you're still going to get 0. Okay? So invariant points with a vertical stretch, underline the word vertical. So it's not for everything. But if you have a vertical stretch or a vertical reflection and the point is on the y-axis, it will not be affected. So this is going to be your invariant point. Okay. This one was challenging a little bit for the other group because now we're going to do stretches on the x. So we have to work backwards when we are given the y. An absolute value function essentially is the same as saying y equals x, but it has to be positive. So if x is negative, you're still going to have a positive output y. So if y is 0, x is 0. If y is 2, then x is 2, or what's the other possibility? Or -2. Yes, thank you. -2 or +2. X can be whatever it wants, but because it is inside these absolute value brackets, the output must be positive. So there's multiple options. Okay, and so if y is 4, x is also 4 or -4. All right, so we're looking for a V shape. 0, 0, 2, 2, 4, 4. Negative V shape. Okay, so now we are going to essentially do the same thing, but we are doing it to the x component. Working backwards sometimes is a little bit challenging. So we are replacing x with something next to the x. Now remember, on the last page, the first page here, I said I'm replacing y with 1/2 y. And then when I isolate it, it goes to the other side and it becomes a 2y. When we do this with x, though, we're not solving for x, so it is what it is. So whatever coefficient is going to be on the x, you're thinking about the reciprocal. Because with y, 1/2 y is an expansion by 2, and we'll see it when we solve for y. But we're not going to be solving for x. So we always have to think x is the opposite of what we see. So it's going to be the reciprocal. Okay, so going down to our page here, don't get too dizzy. Here, y equals 1/2 x. This is telling me I'm going to have an expansion by 2. It is the reciprocal. And this is how we're going to think of it. We know that 0 is 0 is going to be true. But when I look at y equals 2, that means I put something in here, I divided it by 2, and I got 2. So what divided by 2 will give you a 2? 4. And because this is an absolute value function, what's the other possibility? -4. And so in order to get 8 by dividing, sorry, in order to get 4 by dividing a number by 2, it must be an 8, right? So I'm working backwards in my mind. What did I do to get the y? I divided by 2. So to find the number, I multiply by 2. All right, let us graph this. So 0, 0, 4, 2, and then 8, 4. 4, 2, 8, 4. Okay, I want you to think of a horizontal expansion as, pretend your arms are up. If your arms are up make it look like the pink graph, right? 45-degree angle, and someone is stretching you out, right? Your arms are going to get stretched out because they're pulling you in both directions. So an expansion is getting stretched out to the left and to the right. And the opposite is true with a compression. Now I have a 2 by the x. So 2 times something is going to give me a 0. Must be 0. 2 times something is going to give me a 2. What did I multiply? 1. Or -1 in this case, because we have absolute values. To get to a 4 by multiplying by 2, I must have started with a 2 or -2 in this case. Okay, so when I go to graph this, 0, 0, 1, 2, and 2, 4. Again, imagine your hands up as if you were displaying the pink graph, your base function. And somebody comes up and compresses you. This is a compression. They're squeezing your arms. So you're going to get, your arms are going to get closer together, right? So a horizontal compression is when you get squeezed together. A horizontal expansion is when you get stretched out. So just imagine what your arms are doing, okay? Always working back, not backward, but reciprocal when dealing with the x's. Similar when we did the translation, right? We have x minus h means to the right, x plus h means to the left, right? And same with the expansions and compressions. X is our special little snowflake. Okay, let's take a look at mapping. If my original function is xy, what have I done in A? It looks like I multiplied by 3. What did I actually do? I did 1 over 3. So I took my x and I divided by 3. So when you substitute that coefficient, by the time you put it into your equation, you are doing the reciprocal of what you see when it's next to the x. Okay, what about B? I start with xy. What did I do? 4xy. Awesome. Okay, let's look at C. I started with xy. What am I doing? Negative 1 over 2x. You could also write this as, well, let me just switch colors here. You could also write it as negative x over 2. That's the same thing, right? 1 over 2x and y. Okay, also a reminder, this means I'm doing 2 things. I have a reflection over the y-axis, meaning it's backward. Backward. And I have a compression. I'm dividing it by 2, meaning I'm making it smaller. Okay, last one. I start with xy. Pay attention to where everything is. What is my mapped coordinate? 4 over 3x, negative 7y. Okay, focusing on this, Let us talk about all the things that we're doing to this graph. What's happening with the x? Horizontal. Why did you say expansion when I see a fraction? 4/3. So it is bigger than 1. We are getting bigger. So it's a horizontal expansion. So that's the one thing we're doing. What else are we doing? Reflection where? Over the x-axis. So it's upside down. And what else am I doing? What is this 7 telling you? Vertical expansion or compression? Is it bigger than 1 or less than 1? It's an expansion, right? 7 is bigger than 1. So in this example, I'm doing 3 things. I'm expanding it sideways, I'm expanding it vertically, and I'm flipping it over. Okay, as an exercise, I would like you to, on this last page, on top of the graph, okay, this is XY. I want you to tell me what is the mapping of each one. What would the mapped coordinates be? Is this your next page? Yeah, it is. Sorry, I flipped up ahead too far. Okay, talk to a partner. I want you to write down what is the mapped coordinate. Your original is a weird line there. Broken line, I should say. Okay, once you have your mapped coordinates, I have just written down what the original coordinates are. I want you to go ahead and draw what the other 3 graphs should look like based on your mapped coordinates. Take a minute. When you're ready, the answers are on your screen. Double check that your mapping is correct. Double check that your pictures are correct. And if you're done all 3, I want you to identify the invariant point and what is the rule when we're dealing with horizontal stretches. I can't use a ruler on this thing, so my lines are a little bit crooked, but hopefully you can see most of it anyways. Okay. Invariant point, which one? The middle, 0, 5, right? So when looking at this specific graph, our invariant point is 0, 5. So our rule when dealing with horizontal stretches, whether it's an expansion or a compression, any points that lie on the y-axis, meaning if your x is 0, then no matter what you do in terms of stretches or reflections, they will not be affected. I'm going to save that last paragraph for Monday's class. I'm going to do a little side note here so that you have it on your screen and in your notebook. You should have done question homeworks from 1.1 and 1.2 from the textbook. So you have the PDFs on our Teams, and you should have at least attempted some of the Delta Math. Okay, try the level 1 and level 2 stretches assignment. I think it's called stretches and compressions or something like that. All right, even if you did every single question on Delta Math, including the translations, total, it would only take you 2 hours up until this point. And I say only because I'm not wanting you to do 2 hours straight. That would be ridiculous. You're doing, at this level, 20 to 30 minutes a day. That would get you to an hour and a half. That's the majority of the questions, okay? You're aiming for 3 in a row correct. If you get the first 3 in a row correct, it was too easy. Move on to the next one. You don't need to do all 10, okay? All right.